All right. Hello, everyone. Hey, hey. How you guys doing? Doing pretty well. My in-laws were in town over the weekend, which was fun, but it's always just a little bit exhausting because I'm not a people person, so I'm just ready to be quiet and alone for once. But here we are. Okay, so today I want to talk about point of use technologies and really start getting into kind of technological interventions that we could consider. But I guess before we jump into that, I do want to remind you that I'm asking, I sent an email today, but I wanted to remind you to go to our research paper part of Moodle, or to take a look at the email and follow the link. That'll bring you to this Google Doc, which last week I had not properly allowed everybody to view it, or only been viewing, not editing as well. So please fill in your, wherever you'd like to essentially take a topic there, please do so. That's essentially what I'll do for attendance today. Is if you've done this by the end of today, then we're good. And you'll get, I'll just mark that as everybody who has done so has credit for today. Of course, it's not the end of the world if you happen to do it tomorrow, but it's nice to have the deadline so that you can have enough time to prepare for your kind of first task, which would be essentially writing that first paragraph, looking at a bit of literature, kind of looking at what argument you want to make about your topic and formulate that argument. Then we'll have everybody kind of do a speed presentation sort of thing. Here's my thesis statement, maybe a sentence about what you're the category, and then here's my thesis statement. And that'll be a presentation of sorts that we'll give each other some feedback on, and we will kind of use that as a guidance tool to say, maybe you can strengthen your argument or make it a little more specific, or maybe it needs to be more broad, something like that. Okay, so that'll happen on the 23rd. I heard that the academic program's a broad person. She sent me an email Wednesday morning, and I was packed. My schedule was packed that day. She was asking maybe could we meet at 11:30 on Wednesday, which is right before I taught, and I had meetings and stuff, so I didn't even get to that email till later. So I don't know if that's good or bad news that she was like, hey, can we touch base about the Nicaragua trip? But presumably I will hear soon. I need to ask them also about the status of putting in, the system was closed, so you couldn't put names in. So I'll be bugging them again this week, probably later today, about that. Otherwise, no updates as far as that goes. I did add some writing resources to this research paper, and I changed the name so it's research paper and writing resources. So definitely take a look at that as you begin writing. We'll talk specifically about some of it, but basically what I started noticing when I was past couple times teaching this class and another class where I had writing assignments, there's a lot of common mistakes. Undefined pronouns. If you start a sentence with it or this, but you're relying on the reader to think back 2 sentences ago what this is, you yourself can get confused and think it makes sense when it actually doesn't. And it really slows down the reader to say, wait, what are they talking about? What is it? And so that's a big one that if you can fix that problem, your writing will be so much more clear regardless of what you're writing about. So a few things like that. Take a look. We'll talk more later, but those are posted now that I found my old website, or my old Moodle. It's like Moodle.3 or Moodle3.lsu, not just Moodle. So, yeah.
The last link, the ACS style guide, I clicked on it this morning, and I don't know if it's just my computer, but it says like the page is not found.
Okay.
I don't know.
Looks like it's my computer too.
Okay, well,
so
I like searched it, and like a ton of options came up, so I wasn't quite sure what.
I'll fix that. It is a good one. If you look at the exact link that it's sending you to, it looks like it's chapter 4 of the ACS style guide. So I'll tell you more about that later. I'll fix that link. so that you don't have to worry about searching for it and trying to find it that way. It's essentially ACS is the American Chemical Society, so there's a lot of journals underneath that, and it's a high quality publisher essentially for scientific work, and so they have a very comprehensive style guide for what's typical formatting for kind of research type writing. So again, more on that later, but for now, unless there are any questions about that, we'll go ahead and get to our point of use technologies. All right, so how many of you have thought about getting a new phone or a new device of some sort and thought to yourself, so raise your hand if it was like super excitement about the newest thing. Okay, some people, all right. How many of you are like, do I have to? So you can imagine, and probably every one of us has that uncle or someone like it who's like either super into the latest, the greatest, the every detail about that thing. Maybe it's your dad, maybe it's your brother, who knows? Maybe it's your sister, or maybe they're on the reverse side, and your other uncle is just like, no, I'd still rather have a typewriter in front of me because I can feel it. There's kind of a spectrum of how people interact with new things. And part of that's just simple psychology, right? Change is not always comfortable. In fact, a lot of times, if you're asking somebody to do something new or change their behaviors, it's just there's some inherent hesitation or like, I know how to do it. I know how to get by with what I've got, right? There's that element there. So business psychologist types have identified categories for the bell curve of people. So if you look at the how quickly people adopt new technology, you can probably sort yourself into different places. And maybe this changes if your life is super stressful. Maybe you just sort of don't have time for it and end up being in sort of the more skeptical or conservative, like just in the like I don't feel like changing type meaning of the word. Instead of maybe those innovators or the early adopters kind of categories, right? So just kind of mentioning this because you can expect that if you go in bringing a new technology to treat water, this is going to happen, right? This is going to be the same thing going on with the local community, kind of no matter wherever you are. It's a human nature sort of a thing. So as you think about it, you might actually benefit from identifying some leaders in the community who have the time and energy and interest in engaging in something new and helping spread that and overcoming this little, they call it the chasm, if you look closely. Essentially, what we need in order to have a community adopt something, you end up needing at least some sort of a majority, right? Some community buy-in. If you think about in actually just sort of a developed context, high infrastructure context, we actually we tend to be very conservative or skeptical in the water treatment industries because we don't want to have any risks to the service of clean water, right? That's a big and important thing. So actually the industry itself tends very much this way, whereas kind of point of use offers a little bit more in terms of early adoption. Maybe we made a little lid for my water bottle one time where you put a little UV LED and then a little battery pack on top and attach that and then see how quickly it disinfects your water. So that's something that we could do, and something that there are some companies that have done that already actually. And that's easy to try and test to see if it works and discard. It's not like you're treating water for millions of people and saying, oh, this better work, right? So the operators you'll find are almost always fairly skeptical. If they know how to do it, they know how to do it safely, they know how to fix it if it breaks. There's a lot of motivation there for how it's done right. That's going to change a little bit in maybe a developing context. People might recognize that their water is pretty dirty and look for anything to improve it, especially if you can provide some sort of a tangible or visible change in the water quality. So probably treatments for turbidity, kind of the murkiness of water, that's going to be probably one of the the easiest buy-ins, right? 'Cause you can just see it. That's cleaner, right? So that can be a benefit. Education about the germ theory of disease is probably a great way to start that buy-in process, right? If people understand there's stuff you can't actually see here, maybe you bring some low-tech microscopes where you could visualize some of the microorganisms in the water, something like that, to get people to recognize the importance, right? So if you can make that tangible, that's super helpful. And from there, again, thinking back on, okay, I'm gonna provide you with a new personal computer, but I'm gonna give it to you in components. How many of you would be happy to go ahead and assemble that and have a brand new computer? Any of you computer nerds like myself? No, not a one. Wow. So I have an old laptop that I bought. I think it might have been on eBay, but it was like the laptop shell, but it didn't have a hard drive, didn't have a processor, didn't have memory, or a Wi-Fi card. And so I bought those components individually the way I wanted. Maybe I wanted a very fast processor. I didn't care for a lot of space on my hard drive or whatever. I could make those decisions. So I assembled it all together. And then several years later, I noticed some smoke coming out of the back. I was like, uh-oh. So months after that, I finally found a solution and essentially did like heart surgery on my laptop. And it still works. It's not this one. This one's a little bit newer. And I customized it, but I didn't bother putting it all together myself because I got somebody else to do it. So anyway, that early adoption, right? If you have the interest and the skills or you have the education to put the thing together, you're happy to use it. If you're like, well, where the heck does that go? You're not going to use it. You're not even going to be happy about it. It's like, well, shoot, now I have this thing that costs a lot that I'm supposed to like, and it's just going to sit there collecting dust for a year before I try to get a friend to help me with it, right? That would be, you can imagine that that's going to be how it is if you give somebody some technology and with no instructions or minimal instructions or whatever. So my dad's a computer programmer, so I grew up back even in the 90s with these big chunky computers, and we were always tinkering with stuff, so it was never a strange or weird thing for me. So anyway, the point there is if you have a technology that's intuitive to operate, and sedimentation is fairly intuitive, we'll talk about it today, that's really helpful, right? So that's going to be one of the things that are really key. I've heard stories about people putting in, let's say, a nice well pump. The system works, everything's working except the handle broke, and without the handle you couldn't turn the knob to turn it on or off, and so then the community just stopped using it, and it becomes a latrine instead of a source for fresh water or whatever. It's like things like that happen if you're not careful with how easy it is or how feasible it is to implement, to maintain, to repair. All of these things are really important considerations there. Anybody have any funny technology stories? Something break? Should have been an easy fix? Nothing? Yeah.
One of my roommates, he likes to build computers, like you, I guess. And he had one like a year ago. I think it was like his graphics card or something like that, and pretty much caught on fire and put his computer in flames in our old apartment.
Oh my gosh.
Yeah. That was like probably a year and a half ago though.
Sounds like maybe he overclocked it a little too much.
Yeah, definitely.
Heatsink wasn't adequate. That's crazy. Yeah, fortunately my laptop didn't get quite to that point. The thing that happened was the place where my power connects to the motherboard, so the little power jack. Of course, Apple computers have little magnets that kind of fix this problem to an extent, but the inside of it, there's something that has to hold and grip that. So if you knock it too hard, you can knock that connection loose. So then I was having a short circuit where it had been knocked one too many times, and it was that little spot was really not making a good connection, so it got arcing across and just burned a little hole in the motherboard. Okay, so on to sedimentation then. Essentially, the aim for sedimentation is to use gravity, right? Most of you, if you've taken 3110, you've probably seen this before. I'm just going to do a quick derivation of the math we use to describe sedimentation. Some of you, I don't think, have taken this class. Maybe you're visiting from another major or whatever. So I'm just going to do a quick kind of recap of it. We'll do a kind of an example problem just to get a feel for how long would it take for like a silt or clay particle to drop from the top of a 55-gallon drum where you might be storing your water. How long does it take until that particle sinks to the bottom with some kind of reasonable conditions? Just to take a look at what's practical, right? And it turns out the forces that are important for sedimentation are relatively straightforward. It's like skydiving. You know, you have a acceleration due to gravity, so you're dropping. You have some force of drag against you, so then you'll find a terminal velocity based on the balance of those two. In this case, in water, we also have a buoyant force, which we don't really think about in air. It's kind of the amount of the mass of air we're displacing. We have a tiny, tiny buoyant force of that air on us. In water, obviously, that becomes a lot greater because water is a lot heavier. So we can describe those three forces as a buoyant force, say FB, force due to gravity, FG, and then we end up with force of drag opposing the direction of travel. So assuming we are sedimenting rather than floating, which sometimes you could do it in a fancy air bubble flotation sort of thing, probably not practical for point of use. So you could potentially float particles, but that force of drag then would be a force heading upwards. And so ultimately, we'll get a force balance, and when the net forces upwards equal the net forces downwards, we have a constant velocity. And that's what we're looking for. And essentially what we're going to do is, even though particles are misshapen and weird, we can do some simple math, assume they're spherical, and that gives us a simple way to have a handle on what we're dealing with for an example case. Okay, so we got these, the force of gravity, buoyant force, force of drag, and so we can describe all of these for a spherical particle in the following way. So the gravity is going to just simply be the mass of the particle times gravity, but we're not going to weigh each particle individually, so it makes a lot more sense if we can get some bulk density measurement. Maybe we do some sort of a filtration experiment and see how much weight is in the particles, and maybe some estimate of the size. It's actually turns out to be pretty easy to estimate the size of particles using light. So maybe we get some information about the size and the density, but we don't know the weight of each individual one. So then we calculate, if we get that density, these will all be defined in a moment on the next page. But essentially, we can go from mass times gravity, acceleration due to gravity, to the volume times the density, which is mass, because the density is mass per volume. Okay, so with that, that's essentially what we're going to do. The force of buoyancy is the mass of the water displaced instead of the mass of the particle itself. So then we'll just use the density of water. So we'll have the density of the particle and the density of water as two of our parameters. That's going to be this little rho guy, rho p for the particle and just rho for the water. And then our force of drag is going to relate to the particle size. Again, think about skydiving. If you fan out wide, then you've got lots of surface area, lots of drag compared to, or if you do like the outside the car window thing, you're feeling the force of drag. So you've got 3 times the viscosity of water times pi times the velocity of your particle times the diameter of the particle. So that turns out to be kind of a simplification of the surface area here, and essentially that's head moving through the water, and so we get a drag force like that. Okay, so all of these things written up here, kind of explained in a little bit more detail. So each of these terms, that dynamic viscosity with their units, and what we'll notice is really we're using kilograms, meters, and seconds. It's pretty much makes the most sense to work in those units. So we'll end up with a settling velocity some velocity downwards, Vs, in meters per second. And if you think about it, if you have a small particle traveling through the water, falling downwards, it's going to be pretty slow, right? So it's not going to be numerous meters per second. It's going to be a very, very small fraction of a meter per second. It's going to be like maybe millimeters or micrometers per second, right? So it's going to be, in meters per second, it's going to be something times 10 to the minus 4th, 5th, something like that. Okay, so then we've got all of these, acceleration due to gravity. We know that's 9.81 meters per second squared. All these other pieces, and essentially what we do when we derive the equation is we set the force balance like this. The force of gravity equals the force of the buoyant force plus the drag force. And then we can solve for Vs and get the terminal velocity. So we'll do that real quick, and we're going to use it in the terms of where we know something about the volume of the particle or the diameter of the particle, and solve that way. So we'll say volume of the particle times the density of the particle times gravity. That's going to be equal to, volume of the particle times rho times g, all that plus 3 times the viscosity times pi times that settling velocity, which is what we're going to solve for, times the diameter of the particle. Okay, so we can get these the volume of the particle in terms of diameter. So the volume of a sphere, we can define that in terms of diameter, which I think should be 1/6 times pi, is it r cubed, I think, or is that diameter cubed? Somebody check that real quick. Maybe this is diameter. You're going to need a calculator in a moment because we're going to have you do a practice anyway. So somebody could check that. 3/4 pi r cubed. Is that it? 3/4? Guess I can Google it with you. That's what it is, 4/3. Okay. So 4/3 pi r cubed. Now if we take that r and transfer it into diameter, we can say that's going to be equal to 4/3 times pi times that diameter over 2 and cube that whole thing right there. So that gives us, that's going to give us 2 to the 3rd, which is 8. So that's going to end up giving us 4 pi diameter of the particle cubed divided by 3 times 8 divided by 24, and that's where I was thinking the 1/6, right? So that's that gives us 1/6 times pi dp cubed. Okay. All right. Thanks for the help there. Okay, so that means we have a way to get Vp into the diameter, which is nice because our drag force was already in diameter units. Okay. So that's also going to give us pi in every term, so that should probably cancel out. So we'll go ahead and before we do anything else, I'm just going to go ahead and put that in. So I'm just going to write it pi dp cubed over 6 times rho of the particle times g. I'll go ahead and move this to the other side. So I'll just say minus essentially 1/6 again, pi over 6 times rho times g. That's dp cubed equals this 3 times viscosity times pi times Vs times dp. Okay, so we want to solve for Vs, and we just need to simplify a bit and move everything away from the Vs side. So when we do that, we can see if we divide everything by pi, those are all going to cancel, which is nice. If we divide everything by 3, well, first of all, let me just go ahead and factor out some things over here. So on the left side, I'm going to say the g is going to come out of both parts of that equation. So we'll have g, and the dp cubed is also going to come out of both sides. And the divided by 6 is going to come out of both sides here. And we're going to be left with all of that times rho minus rho of the particle. Okay? And that's going to, on the right-hand side, we still have the mu, the Vs, and dP. So then when we divide both sides by all that to give the Vs, we are left with our acceleration due to gravity. I'll go ahead and put that times rho minus rho of the particle. We're going to be left with the diameter of the particle squared here because we had it cubed divided by it one time. And then, excuse me, I should have kept the 3. 3 was still there. If we divide both sides by the 3, that gives us 18 on the bottom, and we have to get rid of the mu as well, so we have 18 times mu. So that's our equation for Vs. This is, again, there's a few assumptions going in here. Essentially, it's a spherical particle. We have kind of a very still or maybe laminar flow, if anything, system. And then we're also assuming all the particles are the same size, right? So there's quite a few assumptions here to describe this velocity. But once we do that, we have a relatively straightforward equation that we can use to figure out how long it's going to take to settle some kind of particle, which is really what we're interested in if we want to treat some water and we say, well, it's got silt particles that are this size, it's got this temperature, how long is it going to take? In a municipal scale system, what we would do with this is say, okay, well, we want to treat water continuously, and so we're going to flow water through maybe a sedimentation chamber or maybe some circular clarifier where water is going to travel from the inside radially to the outside, however that, in every direction kind of thing. In either case, what you end up doing with a kind of a continuous flow system is you have water flowing, and you can take a cross section and then describe that cross section. Maybe it would look like this. You describe that cross section like you have a particle that needs to fall downwards while it travels to the side, and then we declare it settled or removed if it hits the bottom. So we're not going to go really any further into that, but that's kind of what we do in a flow-through system. Typically not going to use a system like that for developing countries just because it's a lot of volume that you have to regulate all these things, have a lot of flow. You'd have to have at least something like a swimming pool size of a container for it to make much sense. So we'll just leave it right there. Just wanted to kind of show you that's the math there. In our case, what we're going to be looking at is typically leaving water in a still, quiet tank that's not disturbed, and then perhaps sequencing that a few times to get a certain amount of sedimentation time. And there's a couple reasons for that I'm going to explain, in addition to just the sedimentation. Okay, so let's take this example problem. I have not solved it, and I'm going to ask you to try solving it first. We kind of have all the knowns here. So basically, if we imagine a 55-gallon drum, which is probably about 1 meter high, so we'll take 1 meter depth that a particle has to settle. How many minutes is it going to take for this particular particle to settle, is my question to you. So we've got the formula. I've got a little lookup table. And this is an example, if I do give you quantification problems on the final exam, it's going to be something like this where I kind of coach you to it, provide you the resources. You don't have to, memorize this for the course. I'd rather you focus on the other aspects. And then it would probably be a discussion. How adequate would this be? What would you expect for the outcomes? Do you think the people would adopt this technology? Something like that, right? So it's going to be in a wider context than just solve the problem. But anyway, So how many minutes will it take for all of 0.01 millimeter silt particles to settle out of the solution if the density is 2.2 grams per centimeter cubed and the water temperature is 25 degrees Celsius? So go ahead and give that a shot, and we'll work together through it in a minute. looks like you guys are about there. So, just for fun, let's do a Kahoot. And see how you did. We will not counting this against you or anything. I just so you don't even have to put in your 8-9 number this time, because I'm getting your attendance elsewhere. So just for fun, I want to see your anonymized answers, unless you want to put in your name. If you're daring and you think you can get first place here by getting the right answer entered in first, then go for it. And it's not a problem if you didn't get get a final answer. Just adding a little fun here, a little pressure. All right. Looks like just about everybody's in. I think it'll let you join a little later too. Okay, so I think I didn't set the time, so you've got 20 seconds to choose the right one. It'll be less than a minute, less than essentially 10 hours, so 600 minutes, less than a day, 1440 minutes, or more than that. Okay, I apologize I didn't give enough time to punch in the answer. So, but okay, so I think if my calculations are right, which we'll go through in a moment, I think it's much more than a day essentially. So, all right, so let's see what happened. And I have a theory of what probably happened. Let's see who's got the top score here. We've got a podium here. Well, 0 points. The third place was the fastest that got nothing, right? So is that a honey badger for number 2? All right, there you go. All right, cool. Okay, so I think probably what happened is lookup tables are annoying and tricky, and they put in a little unit right here. So if you didn't pay close attention to the units, you missed that times 10 to the minus third. That's going to throw your calculation way off. So likely that happened. Perhaps some of you were just guessing because you didn't feel like it or whatever. Boring. Okay, so if we want to solve the problem, we need essentially to get all these little pieces and plug them in, right? So we're going to say Vs equals all that. And so let's take a look at each one of them. Acceleration due to gravity, 9.81 meters per second squared. We talked about that a minute ago. Rho for the particle was given as 2.2 grams per centimeter squared. Not cubed. Oh, yes, cubed, sorry. Centimeters cubed. So that density, it's there, but that's not very handy because we need meters and kilograms. We mentioned that earlier. And essentially, it turns out if you go from grams to kilograms, you're dividing by 1,000. And then if you take centimeters, which is, so 1 centimeter equals 0.01 meters. But then you need to cube that, right? If you're going for cubes. And that can get a little tricky. It turns out that that 0.01, that conversion essentially ends up if you do the math for both of those at the same time, you end up with essentially 2,200 kilograms per cubic meter. So you have to do both of those conversions in that one. That was another tricky spot, pretty easy to mess up. The easy way to think about that is pretty much you're always going to be on a scale that's kind of on par with the density of water, and that's given in kilograms and meters cubed, right? So the density of the water is, if it's going to settle, the density of the water has to be less than the density of your particle, so your particle should be a little higher than that, and that should give you at least a way to check to make sure you're reasonable. Okay, so that's the density then. The mu, like I said, 0.89, but in the units it's times 10 to the minus third kilograms per meter per second. And then, let's see, the diameter of the particle, one last one you had to convert, that was 0.01 millimeters. And if you convert that to meters, that's going to be essentially 1 times 10 to the minus fifth meters. And so then you can work with it in that unit. So then, if you put all that into a calculator or into Excel like I did, you should be able to get a settling velocity here by putting those in. I got 7.4 times 10 to the minus fifth meters per second. And then to convert that from, actually I did something wrong. I didn't convert from seconds to minutes, so we'll check on my actual answer here in a moment. Maybe I led you astray. So this will give us, we can take 1 divided by the Vs, because we have 1 meter. 1 meter divided by the velocity should cancel those meters out and give us seconds, and that's what I calculated here. That's in seconds, and so and I need that in minutes, so I need to take that and divide it by 60 seconds per minute. And yeah, totally totally fooled you. I did it wrong. Okay, so it should have been 226. So I think 9 of you actually got it right, and I didn't in my hurry until I worked through it with you here. Apologize for the fake news there. So that should be, we said, it's like 13,000 seconds and some change, or 226 minutes. Okay, so if you did it like I did the first time, maybe you did everything right except the last conversion you needed, or maybe something else went wrong, maybe both of the above. Anyway, so just kind of a quick problem to look at. That's what, 220 minutes. That's close to 4 hours of time before this one silt particle sinks 1 meter through solution. So in fact, if you're going to do it, like maybe have a big jug like that and do a change every day or something, that might actually be reasonable to collect those types of silt particles. Now, to think about it, if we have different contaminants that we're interested in removing, if you think about that 10 millimeters, no, that was 0.01 millimeters, that's essentially 10 micrometers, right? So if we think about how quickly that's going to happen, that's essentially describing anything right here that has the density of a silt particle. So if we look then, we can get rid of some pollen, human hairs, basically the limit of what we can see with our eyes. That's kind of what we're talking about there. Maybe some pathogenic cysts, possibly, and any pathogens that are stuck to these silt particles or dirt particles. And of course, with a little bit longer time, if we give it 24 hours or so, maybe we can drop down a little lower and then get a few more cysts or something. But as you can see pretty clearly, this is not going to be anything reliable for the bulk of bacteria, and certainly not viruses, right? Okay, so given that, there's some consideration, well, what kind of control do we have here? If we look at our equation, unless we're producing artificial gravity, we can't really do that. We don't really change the viscosity very often. Temperature can affect that, but it's not usually something we want to spend the energy to change just to make particles sink faster. Density of the particles, typically we can't manipulate that very well, so it really leaves us with the diameter of the particles. And that's where we'll get into, in the coming lectures, strategies to cause the particles to stick together. So then you form a larger particle, because we've got a dependency here, the speed is dependent on the square value there. So if we double the particle size, we are quadrupling the particle speed, right? So that's a pretty good tool to use. So if we can cause the bacteria to stick into larger particles, that's a really great thing to do. Conversely, if we look at if the particles just happen to be smaller, they're going to be a lot slower to settle. So it kind of works both ways there. Okay, so a few things to consider when we are applying this in a batch system. If you, again, think about having some container, maybe that 55-gallon drum, maybe even a smaller, 5-gallon, 10-gallon carboy or something, and you're trying to cause all this stuff to sediment out, well, one really important thing is if you pick that up, you bump it, you disturb it at all, you're going to be acting like this little clam and kicking up all the stuff you just spent hours settling, right? So in terms of operation, and this is a very easy to visualize, easy to perceive problem, you have to have your operators be careful with what they're doing so they're not kicking that back up, right? And just so we're not staring at that the whole time. If you've ever done anything in the water and kicked up mud, you can really get a feel for that. This is actually one of the reasons why cave diving is so extremely dangerous, because when you disturb anything, all that sediment gets kicked up and then it's very easy to be disoriented. So interesting little factoid, cave divers are it's an extremely dangerous activity. You always have to have a nice guideline and all that. Okay, anyway, so that's a big concern for recontamination. So typically what you'd want to do is have a system where you can withdraw carefully, slowly, water from one bucket or container into a second one, and probably let that one have time to sediment as well. So we'll talk in a moment about it, but most times where you're going to apply sedimentation as a point of use operation, you're going to have at least 2 buckets, probably 3, or buckets, pots, whatever. Okay, so the other concern is really, if you're just relying on this, you're not getting a lot of stuff removed, right? At best, you can think, well, you're getting rid of the suspended particles, there's going to be some bacteria attached to them, viruses will often stick to particles around, so you'll remove some things, but certainly it's not ideal. You don't want to rely on that if you don't have to. I mean, it's going to be better than nothing, so a good idea if nothing else. You also potentially can cause pathogens to just simply expire because they can't live long enough. There's a specific case of the larva for schistosomiasis. It's a pretty bad parasitic disease, but essentially the life cycle for that is it goes from the contaminated fecal matter into water, then it gets into snails. Snails are infected, and then they excrete or die from the infection or whatever happens, I don't remember, and they end up, the pathogen produces larvae, and that larval stage has a 24-hour or 48-hour lifespan. So if you can keep the water out of contact with humans for 48 hours, those are pretty much all going to die off. And so even just letting it sit there, even if you didn't accomplish the sedimentation, which you might as well, that would actually be a good thing. And some bacteria will decay in that manner too. Okay, so that's this pathogen die-off. So if we're giving something 24 hours, you'll get about 50% of bacteria will decay, deactivate, especially if it's hotter. Hot temperatures are not very conducive for bacteria, unless they have stuff to grow on. So if you have contaminated water that's got lots of organic junk in it, maybe you're growing pathogens if it's hot enough. Not so likely. At typical room temperatures, without much food, because it's clean-ish water, you're presumably not going to be growing too many, and if you are, it's probably in that sediment layer you're hopefully removing anyway. Yeah, so it's 48 hours for that schistosomiasis intermediate phase. So really, you want at least 2 pots, and you want to have the water sitting around typically for at least a couple days, if possible. You want to take that water from essentially what we call the supernatant, so anything outside of what's collected on the bottom. If you ever do centrifugation, It's essentially sedimentation. You sped it up by increasing the acceleration due to gravity by doing that centripetal force. So I guess there is a way to increase that one, at least in a laboratory setting. So anyway, we take the supernatant, so that the water up here, carefully pour it off into a second vessel. This would be the 3-pot method, and then to a final one, and make sure we're taking out of that one. And you would clean this one and essentially clean them as often as you can, using some of your clean water, right? So you'd want to be sacrificing some of this clean water to clean out that first pot, especially because that's going to be real dirty, and you don't want to carry that forward, and then this probably you'd want to clean often too, maybe not needed as often. Okay, just wanted to read real quick the kind of through the instructions of operation for this. It's not super fancy, but I wanted to kind of give you an idea of the recommended techniques here for proper 3-pot operation. Okay, so first you take take water for drinking and cooking from pot number 3, all the way on the right. Essentially, it's been stored at this point for at least 2 days. So that's going to prevent, like we talked about, some organisms from living that long. You're going to pour water carefully, so you take it from 3, and so then the third bucket is empty, or it's got some space in it now. So we're going to take from 2 and pour that into pot 3 carefully, wash out pot number 2 using some water from number 3. Pour carefully from 1 to 2, and so this is just physically pouring, right? So you are going to kick up some of the sediments, so you got to be careful when you do that, not to kick up not to pour in all the sediment stuff. After collecting water from the source, pour it into the vessel used for collection in number 1. If possible, use a cloth filter just to add a little bit of something to get the large particles. Okay, so because of the low cost, low level of required skill, sedimentation is an attractive way to pre-treat water, reducing the turbidity. So this is a good concept here. If you can do this and then do a little bit of chlorination, it's going to be a lot better than just starting with chlorination. Or you do this and then you have a small UV treatment or a small filtration unit that's kind of maybe hand powered or something. If you can use this as pre-treatment, it's something that pretty much anyone can do once taught the reason they should care, and they have some buy-in to actually want to use it, right? Would be a pain in the butt to have to do this all day, every day for our own water, right? We would much prefer having infrastructure with a piped tap so that I can just fill this from a water fountain and not think about it, right? That's really nice. But it's a good pre-treatment. It'd be good if you have access to no other treatment. Let's say we have, apocalypse type situation, between fighting off zombies or whatever, you could have your 3 jugs of water and be doing sedimentation to have some sort of treatment for the PoU water that you might have to rely on, right? Okay, I think that's all I have for you today. Again, I'll try to get you updates for the Nicaragua stuff soon. Any questions, issues, comments? All right, so next time I think we'll talk about kind of adding in simple coagulation treatment to this type of concept. I'll look at this also. It might be filtration. Okay, so I'll see you Wednesday.